Fundamental principles of radio telescopes and its relations with the world. Observations have always been the foundation and evidence for astronomy. For centuries, humans have only been able to observe the sky through the naked eye, or small telescopes that only allowed a peek into the vast space. However, the wavelength range of visible light is merely a small segment of the universe's entire electromagnetic spectrum. Radio astronomy bloomed and matured in the 1950s with the help of wartime-inspired scientists with backgrounds in radio science, electrical engineering, and wartime radar. Observing the universe through radio transmissions allowed a much deeper understanding of the universe and its components. The discoveries of quasars, interstellar molecules, and other objects that are too cold to emit observable light were powered by the revolution of radio astronomy. The 1964 Physics Nobel Prize was awarded for the discovery of CMBR, or cosmic microwave background radiation, that was strong confirmation of the Big Bang theory. And this accomplishment was also backed by the technology of radio telescopes. Just like any other basic science, radio astronomy is also facilitating the development of other branches of science. Innovative technologies in radio astronomy have played major roles in today's antennas, Wi-Fi, and even medical fields. These examples prove valuable, and protecting the usage spectrum of radio astronomy is meaningful and important as it greatly depends on a low discrepancy environment. Working principles of radio telescopes. And before we talk about the telescopes themselves, it's important that we understand what angular resolution represents. It's the ability for an optical device to depict details of an object by distinguishing 2 points of an object or 2 objects at a certain distance in the image. In simple words, it's the ability to distinguish 2 points or 2 objects that are separate despite viewing them at a far distance. Imagine if you put 2 plates very closely together and view them from 100 meters away. They could very well seem like they're one plate. But that's because you don't have enough angular resolution to tell them apart. Now, to look at the radio telescope, it has a paraboloid-shaped dish that serves to be a mirror that will redirect all EM waves to a mutual focal point, a feed horn, which is a type of antenna for the reception of microwaves. If we look at the equation of angular resolutions below, it's theta minimum that represents the angular resolution, because the smaller the angular resolution, the better the depiction of observations. So in this case, lambda represents the wavelength of the radio wave, and alpha represents the diameter of the observing objective. So it is noticeable that for a better observation, alpha, or the diameter of the dish, would need to increase. So the size of the paraboloid-shaped dish of radio telescopes greatly determines the quality of its observations. Radio wavelengths are significantly longer than wavelengths of visible light, and longer wavelengths naturally cause resolutions to be poor, and this is one of the major problems of early stages of radio astronomy. After using the dish and antenna for interference, the telescope is connected to receivers and powerful computers to process the radio information into a form easy to understand and record. The general role of any receiver is to select wanted frequencies from the numerous EM waves in space and filter out noises as well as other signals. It is the same for radio astronomy, except with more complex structures and rigorous requirements. Radio telescopes use the world's finest receivers because the quality of the receiver determines the sensitivity, which is the minimum energy detectable, and most of the signals from space are incredibly weak for being so far away. Telescope receivers consist of 2 ends. The front end of the receiver attached close to the antenna amps and converts frequencies to restrict the frequency range for the detected EM wave. The back end measures the power and converts the wave into digital signals for the terminal or computer to store and visualize through complex calculation. VLBI, or Very Long Baseline Interferometry, is one method to overcome the significant budgetary constraints on building one telescope with a large aperture. Multiple radio telescopes at different locations receive the same EM waves from the same astronomical radio sources at different times. but this delay can be calculated according to the physical distance between distinct telescopes. This means that the total diameter of observation would equal the distance between the telescopes, thus greatly reducing the angular resolution and producing a significantly clearer image. This technique drives the establishment of radio telescope arrays of different specifications that could be looked at as one giant telescope. The capabilities of radio astronomy is greatly dependent on the advances of receivers and digital technology. As astronomers push the process of using the most advanced technologies for radio astronomy, its technologies and applications have also been incorporated into other subjects. The following are just a few examples. For medical purposes, radio astronomers innovated the method of using one-dimensional scans to build two-dimensional imageries, and using two-dimensional scans to build three-dimensional imageries. This reconstruction technology is now greatly implemented into modern CT, PET scannings, and magnetic resonance imaging, which are all used to observe the human body for diagnostic purposes. Radio observations measure the temperature of distant cosmic sources, and the same technology and concept could be adjusted for the non-invasive measurements of temperature of human tissue. Another specific example is the detection of skin cancer, which is propelled by the algorithm radio astronomers invented to detect weak signals in the background of random noise. The malignant melanoma cells can be detected with the same technology for their differences in color. Computing technologies. To store, compute, and process the data collected by radio telescopes require powerful terminals and algorithms. An example being the fourth computing language that was first developed for controls and data processing for radio telescopes, but was then used in personal computers, satellite tracking, and robotic arm simulations. For navigation, the invention of radiometric sextant, a small radio telescope designed for ships and planes, allowed accurate navigation on overcast and rainy days. For Earth observation, the interferometric method used in radio observation helped develop passive remote sensing techniques for the measurement of the temperature of the atmosphere and properties such as the distribution of water vapor, cloud water content, precipitation levels, and more. Vulnerability of radio astronomy. Different from most services on the radio spectrum, radio astronomy is a passive service that focuses on the reception of data. The celestials radio astronomers observe are usually billions of light years away from Earth, and their radio signals are incredibly weak and different for sharing frequencies with active services, such as internet or telephone. Except for pulsars, cosmic signals do not have the same characteristics of being separable with noise and interference signals. In the majority of cases, celestial radiation shares the same statistical feature with thermal noises in the atmosphere of the Earth, and the noise generated by the receiver itself. These characteristics of radio astronomy cause it to be extremely vulnerable to interference. As broadband digital modulation becomes more advanced and mainstream, the EM environment at radio observatories is deteriorating every year. Even in secluded areas far away from human activity, it could still be difficult to reach the maximum potential in terms of sensitivity for radio telescopes. In addition, as new broadband technologies and service applications continuously replace others, the environment of radio frequency interference is also rapidly changing. Instead of the peak, high-power signals, these changes result in signals of lower power, which are more difficult to remove for the receivers of radio telescopes. Now, what could we do to protect radio astronomy from all the interferences it's so vulnerable from? One method is to create more radio quiet zones, which are any recognized geographic area that are modified for the specific purpose of reducing or avoiding interferences to radio telescopes. In other words, is to allocate a specific area designed only for the purpose of radio astronomy. And besides locating these radio quiet zones as far from heavily populated areas as possible, placing them in areas that provide some level of natural terrain shielding is also helpful. So for example, some observatories have found benefits to surrounding their radio telescopes by forests of coniferous trees, which, due to the moisture content of their needles, can provide additional protection from the radio frequency interferences from the horizon. Another method is to advocate for more frequency allocations. The ITU, or the International Telecommunication Union, is responsible for distributing radio resources, or in other words, it sets the range of frequencies allowed for different purposes. Back when services such as internet or telephone wasn't as popular, radio astronomy had much more freedom in terms of frequency range for their observations. But as allocations to active services becomes high in demand, observations at many frequencies are severely restricted or not even possible. Because radio astronomers have great difficulty in sharing frequencies with active services and cannot choose their frequencies arbitrarily, radio astronomy is not easily accommodated within the system of allocation and regulations. Therefore, it is important to fight for more frequency allocation for the purpose of radio astronomy alone, instead of for the mere purpose of profits from internet and telephone.